Institute of Aeronautical Engineering Autonomous Dundigal. This is my tech talk. My name is Venkat Sai. Rule number 23951802226. Subject Electrical Drives and Static Control. Topic Analyze starting current reduction techniques for induction motor in drives. Department Electrical and Electronics Engineering. Tackling Indush Strategies for Reduction Introduction Motor Starting Current. A comprehensive guide to manage motor starting characteristics in industrial applications. The challenge: why high starting current matters. When induction motors start, they draw 5 to 8 times their rated current for several seconds. This induced current, while necessary to establish magnetic fields, creates significant challenges in industrial environments. Excessive starting current causes voltage dips that affect other equipments, increases stress on motor windings, tips protective devices unnecessarily, and generates heat that reduces motor lifespan. In facilities with multiple motors, cumulative effect can disabilities entire power systems. Key concerns: power quality degradations, increased energy cost, component stress, and where system reliability issues. Overview of induction motor starting characteristics. Understanding the physics behind motor starting behavior is essential for selecting approximative reduction techniques. Rotor at standstill. When stationary rotor has maximum slip 100%, magnetic field cut rotor bars at maximum rate, including large currents and creating strong opposition magnetic fields. Locked rotor current. Initial current limited only by stator winding impedance, typically 5 to 8 times full load current. This represents the maximum electrical stress on the system. Acceleration phase. As motor accelerates, slip decreases and current reduces proportionally. Time to reach full speed depends on motor design and load inertia. Steady state operations. At synchronous speed, slip approach 0 to current settle at rated value. Motor operates efficiently with minimal electrical stress. Direct online starting, the baseline problem. Direct online represents the simplest and most economical starting method, connecting the motor directly to full line voltage. While cost effective for small motors, it's the benchmark against which all reduction techniques are measured. How it works? A conductor loss is applying full voltage instructing motor draw locked rotor current until acceleration reduce slip. Starting time typically ranges from 2 to 10 seconds depending on inertia. When it's acceptable, small motors less than 7.5 kilowatts, robust power supply systems, light starting loads, infrequent start current. Soft starters, controlled voltage ramp up. Soft starters employ solid state electronic to gradually increase voltage during startup, reducing induced current while maintaining simplicity. Initial voltage reductions start at 30 to 50% of the line voltage, limiting initial current to 2 to 3 times rated. Controlled ramp up. Thrusters phase controlled voltage increase over 2 to 30 seconds. Full voltage applications. Shorting conductor bypasses electronic at full speed. Advantages: reduced starting current 2 to 3x rated. Lower cost than VFDs. Simple installation and programming. Reducing mechanical stress. Compact footprints. Limitation: no speed control affect startup. Fixed acceleration profile. Heat generation during ramp up. Harmonic on power supply. Variable frequency drives. The ultimate control. Variable frequency drives represent the most sophisticated solution, converting income AC to DC and back to variable frequency AC, providing complete control over motor starting and operating. Rectification: convert AC input to DC using diode bridge, DC bus, filters and stores energy with captures. Motor control: adjust speed to torque. In IGBT transistors create variable frequency. Auto transformers and star delta starting, historical and Nike solutions. These electromechanical methods predate modern electronics but remain relevant in specific applications where simplicity and reliability are paramount. Auto transformer starting. Use taper transformer to reduce starting voltage, typically provide 50%, 65% or 80% of full line voltage. Motor started at reduced voltage, then switches full voltage affecting the begins. Star delta starting. Initially connects motor windings in star configuration, reducing voltage to 58% offline. Then switches to delta, reducing starting current to 2 to 3x rated. Comprehensive analysis, cost, performance, and applications. Each starting method offers distinct advantages depending on applications requirements, budget, cost, and operational needs. Direct online cost 0 to 200, starting current 5 to 8x rated, control none. Best for small motors, robust supplies, simple applications, soft started. Cost 300 to 2000, starting current 2 to 3x rated. Speed control startup only, best for 7.5 to 500 kilowatts motors, moderate budget, reduced stress. Variable frequency drives. Cost 500 to 10,000 plus. Starting current 0.5 to 3x rated. Speed control full range continuous, best for precise control, energy savings, all motor sizes. Star Delta 200 to 1500, starting current 2 to 3x rated. Speed control none, best for European installation 5 to 90 kilowatts, budget applications. Practical considerations and implementation best practices. Load analysis. Calculate load inertia and starting torque requirements. High inertia loads benefits most from reduced current methods. Document existing power supply capacity and voltage regulations. Power quality assessment. Measure voltage dips during motor starts. Multiple motors may require staggered starting or power factor correction. Consider harmonic filters with electronic starters. Thermal management. Ensure adaptive cooling for soft starters during ramp up. Variable frequency drives generate heat requires proper ventilation. Verify motor thermal capacity matches starting duty cycle. Programming parameters. Optimize acceleration, time, and current limits. Avoid excessive ramp times that increasing heating. Configure proper overload protections and fault responses. Maintenance requirements. Electronic required periodic capacitor check and cleaning. Mechanical starters need contactor inceptions and replacement. Document settings and create backup configurations. Safety procedures. Implement lockout, tagout during maintenance. Verify discharge of capacitors before serving. Provide clear emergency stop provide procedures and training. Installation tip. Always size cables and protective devices for the actual starting methods used, not motor full load current. Consult manufacturer specifications and local electrical codes. Key takeaways and next steps. Access your applications, evaluate motor size, load characteristics, and power supply capability before selecting starting method. Consider total cost. Factors in energy savings, maintenance, and equipment protections were comparing initial investments. Balance performance and budget. Match starting methods to operational requirements while staying within financial constraints. Plan for future needs. Consider whether speed control or process optimization may become variable later in operations. When to choose each methods, DOL, small motors, simple applications, soft starter, balanced cost performance, variable frequency type, precious control requirements, star delta, budget European installation, implementation checklist, review motors, nameplates data, analyze load characteristics, verify power supply capacity, program optimal parameters, document settings. Thank you.